You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Ward Howard. Dr. Howard is a NASA Sagan Fellow hosted at the University of Colorado Boulder. He uses space and ground-based telescopes to investigate high cadence multi-wavelength emission from large stellar flares called superflares across the sky. He carried out the first multi-year high cadence superflare survey of hundreds of the brightest and nearest M dwarfs in the southern sky. One of these large flares was detected from Proxima Centauri, which hosts the nearest potentially habitable exoplanet. The Proxima superflare would have delivered potentially germicidal levels of UV radiation to the surface of an unprotected planet at the distance of Proxima b.
Dr. Ward Howard, welcome to the program.
Hi, John. Thank you for having me.
Now, Ward, red dwarfs, have been an object of a lot of discussion within astrobiology over at least the last 5 years, and probably much longer than that. And as we've learned more, we have learned that these things can be very nasty customers with extreme flaring, That's
a great question, John. I think my favorite quote on this topic, I believe, is by John Gizis at Maryland. He would say that red dwarfs are like toddlers. They're never quiet, and when they are, it's not for long. And so I'll start from there and say that very young red dwarf stars, or M dwarfs as we call them as astronomers, are much more active than our older red dwarfs. But even old red dwarfs, even up to 10 billion years old, are still extremely active in terms of their X-ray and UV emission. For example, Barnard's star is a good example of that. And a study in the FUV, or the extreme ultraviolet, showed that star was still emitting a significant amount of extreme UV radiation, even at 10 billion years, that could potentially desiccate a planetary atmosphere, for example. So you start out with a very young, rapidly rotating, very quickly spinning red dwarf star, and then throughout what's called the pre-main sequence, the first about 200 to 300 million years of that star's life, the star is spinning down, which means it's rotating more and more slowly as it transfers its angular momentum into its stellar wind and earlier into its disk. And eventually, the star will slow down from a rotation period of sometimes less than 1 day, where the magnetic fields are very, very intense due to the combined effects of rotation and convection, all the way to very slowly rotating stars such as Proxima Centauri, which has a rotation period of about 90 days, as best we can tell, although there's some debate on the exact period of that star. Does that help to answer your question? Also, higher mass stars spin down or age more quickly than do lower mass stars. So, for example, a star like AU-MIC, which is an M1 dwarf, will spin down more quickly than a star like Trappist-1, which is an M8 dwarf.
So, convection. Now, red dwarfs are fully convective, which incidentally gives them the virtue of great potential age. I mean, trillions of years, because they have the availability of all of that hydrogen. So does that play in? In other words, is the reason these things are flaring so much, is it heavily dependent on that convectivity?
Surprisingly, it doesn't seem to be. And I do not understand this any more than you or any other flare researcher. When we first started looking at flare rates, everyone thought, we'll see major changes at the fully convective limit, which is around a mass of 0.3 or so solar masses. And the flare rates seem very consistent on both sides of that limit, which is surprising, but I think it just says that what's going on in terms of the convective shell seems to be more important, and the surface magnetic activity seems to be more important for the flare rates than the specific transition between the core and the convective layer that you would see for an earlier star such as our sun.
So now, in comparison to the sun with the flaring, of course, our star flares, but maybe once a month, and usually it's not pointed in our direction, it's pointed somewhere else. And when it is pointed in our direction, that's a problem, but not really a problem for life on Earth itself, just our technology. But in the case of a red dwarf, these things flare titanically, constantly, some of them anyway. So give us an overview of what a red dwarf like Trappist-1 looks like as far as flaring each day.
Sure. So Boulder is actually a great place to answer this question from, because we have the Space Weather Prediction Center here, which assesses the effect of coronal mass ejections and geomagnetic storms that arise from solar weather. And as you may be aware, we're approaching, so the sun has an activity cycle of 11 years, and we're currently approaching the peak of that cycle. So right now, the sun is actually very active compared to where it was, say, 5 years ago. And right now, the sun emits what are called X-class flares, approximately one of these a month, as you stated. And an X-class flare is a flare that's sufficiently large till it's usually going to have a coronal mass ejection associated with it. And if, again, the Earth is pointed in the same, or if the Earth in its orbit is in the same direction that this event is emitted from this X-class flare, then that will potentially induce a fairly strong geomagnetic storm and give beautiful aurora. And that's the job of the Space Weather Prediction Center here. TRAPPIST-1, on the other hand, emits an X-class flare several times a day, about 3 of these a day. And that's also true for Proxima Centauri and many, many, many others of these M-dwarf host stars to these exoplanets that the James Webb Space Telescope, or JWST, is searching for secondary atmospheres around. And a secondary atmosphere just means not a hydrogen or helium atmosphere, something with maybe nitrogen or carbon or methane or so forth.
Just as an aside with space weather from our sun, are we in danger? I mean, if we take a direct hit and we get hit, I mean, are our power grids to this day still not prepared for that?
We wouldn't be having this conversation right now if we had just been hit by one of these events. The closest we've come recently was 2012, and Earth was 9 days in its orbit past the direction of a very, very large CME that would have been roughly comparable to something called the Carrington event. Back in the 1800s, the Carrington event is the largest geomagnetic storm and solar flare that's occurred in recorded scientific history. And this event was significant enough to there were worry as far south as Florida. You could operate telegraph wires even if they weren't, plugged into a source of power. We didn't have an electrical grid or telecommunications network like we do today. And there's studies showing that if this particular event or the 2012 event had hit us, it would have caused mass blackouts, major damage to, space technology, major damage to the grid. It would have probably taken several months to recover from fully. And the damage would be probably around $3 trillion for just the US economy. And you can multiply that by all of the other economies in the world economy. And at least before the COVID-19 pandemic, that sounded like a lot of money. And I suppose it still is. But it's something we definitely need to take seriously, even on a smaller scale. I mean, maybe familiar with Starlink satellites?
Oh, yes. Perhaps a little too familiar.
A little too familiar. So several Starlink satellites were actually lost because they had not accounted for this sort of space weather. And the atmosphere was essentially puffed up from one of these auroral events since the sun is in its more active phase. No one talked to a solar physicist, apparently, before that particular launch. And as a result, they had greater drag than anticipated, and they lost the payload. So that's another example where it's really important to think about the dynamic connection between a star and its planet's atmosphere.
That's amazing. So when a solar flare hits, Earth's atmosphere puffs in response.
A little
bit. What's the mechanism? I guess it's just increased particle interaction. What's going on there?
I'd want to go back and take a look at that to get back to you. But I was thinking of it more as just an example of the way that the atmosphere could respond. But I know that there can be changes in the atmosphere's scale height, and that's mostly due to changes in pressure and temperature that result from the increased UV and particle radiation.
Now, in regards to the Great Carrington event, there are many stories about that, about telegraph operators actually having activity on their lines, during this and the solar storm hitting us. But we were still relatively primitive at that time in the mid 19th century. So they didn't really have the technology. But would they have seen just astonishing auroras as the atmosphere reacted to that particularly bad event?
Just from the Carrington event, absolutely. Again, it's very rare to see aurorae that are visible from, say, Florida or Cuba. And it's even more interesting to realize that a lot of people were waking up thinking that it was dawn, or the roosters were crowing because they were assuming it was dawn in the middle of the night due to this event.
So now this gives us sort of a baseline to run with it as far as asking questions about exoplanets, because Earth is someone else's exoplanet. And, we're relatively protected from the sun. Our technology, not so much, but as far as Earth's surface and life itself, we're well protected. But we're around a quiet star, which is a completely different class from a red dwarf. TRAPPIST-1 and the planetary system there, the great discovery of a number of Earth-like planets, these are much, much closer in. They're right next to that star, orbiting just in days. And presumably they're getting bombarded. But there was work a couple of years ago that suggested, by solar physicists, that suggested that maybe that the flares don't actually go out on the ecliptic plane of a red dwarf, but they go out closer to the poles and maybe missing those planets. Can we verify that with the work you're doing? in looking at these solar flares on the red dwarfs and characterizing them, can we figure out if they actually are hitting the planets, or if they're getting lucky and the flares just don't hit them directly?
Absolutely. So I think the study you're talking about is one by my colleague, Katarina Illen. And in that particular study, they were looking at some of those very, very young M dwarfs I was talking about that are rotating very, very rapidly with rotation periods faster than a day. So the sun takes, many days to rotate, but these particular red dwarf stars in that study are rotating so rapidly that they complete an entire rotation in less than a day. And it's not surprising that you would find polar spots and flares being emitted at polar latitudes with very, very large, what are called dipole dominant fields, as opposed to a more messy magnetic field configuration, such as, say, like an octopole, where you have lots of different centers of activity. And so I suspect that that particular result is going to be very dependent on the age of the system. And in fact, Ekaterina has recently published another paper using a statistical framework to follow up on that earlier study that is applicable to older M dwarf stars. And I've not had a chance to fully review that paper yet, but I'm really excited by the progress, and I think it's an amazing technique. In terms of Trappist-1, the benefit of that system is that because there are so many planets that are on the ecliptic, you're able to actually see the effect of what are called spot crossings. And so you can assess the effect of what direction the flares may be preferentially emitted from based on whether spot crossings occur at these latitudes or not, and how frequently. So that's a good example. Another example would be HAT P11, which is Brett Morris's favorite star. That one is another example where there are lots and lots of spot crossings that have been used to map the active, latitudes of the star.
That's interesting. So that you actually can make headway into it. With Trappist-1, now we have the exquisite new JWST, and we have Hubble, and we can start to try to tease out characterizations of atmospheres around these stars, of the planets around these stars. Now, it seems to me a good way to trick an instrument like that is these solar flares and see things that aren't actually there. Could you give us an overview of how characterizing the flares from these stars will help us to eliminate the noise from exoplanet atmosphere characterization?
Certainly. So taking one step back, the reason prior to the launch of JWST that we were so excited about the Trappist-1 system is that it has not one, not even three, but 7 Earth-sized planets that transit the host star that can be, assessed via transmission or transit spectroscopy to sniff out those planets' atmospheres. And 3 of those planets are in what we would call the habitable zone, which is the distance from a star where a liquid water ocean could exist in the presence of an Earth-like or similar atmosphere. So there was a lot of interest in this system. And then furthermore, it's one of only a handful of stars that are both near enough and small enough to we could potentially actually have the signal to noise with JWST to even be able to assess the existence and composition of these atmospheres. So there are very, very, very few of these stars. Each of them is the subject of numerous JWST programs because there are just so few that are bright enough to have those really nice signal to noise measurements. So within that sample, Trappist-1 was the clear, far and away winner because of all of its, properties that make it such an ideal star. And as we started, turning the telescope to it and observing it for hour after hour and transit after transit, suddenly we realized about half of those transits are contaminated by very large solar or stellar flares. And so I like to compare this to that moment in The Revenge of the Sith when, Anakin Skywalker has betrayed his path from the light side and is lying, on this lava planet, and Obi-Wan Kenobi says, you were the chosen one. And, Trappist-1 was supposed to be our chosen one, but it has a dark side.
Yeah, but that's going to be a problem with any of them, right? I mean, if you're, you only have so many that you can, like you said, instrument data quality that we can capture. You can't look too far away, because the further away you look, the less, you're going to be able to discern out. So we don't have a whole lot of other ideal red dwarfs. Now, what would be a good alternative that we could look at that we know has an exoplanet that's close enough to try to characterize so that we can compare that to what we see at Trappist-1?
One other thing about Trappist-1 is we kind of expected that the inner planets probably had lost their atmospheres due to this activity. And the fact that we have not detected atmospheres from those planets in the observations of them that have been published is not a deal breaker for the planets that are further away and therefore slightly less affected by the stellar radiation. Those results for Trappist-1, G, and H have yet to be published. And I'm going to remain hopeful until those do come out. But moving to some of these other more quiet systems, different red dwarf stars have different personalities. It's one of the reasons I love these stars. They cover an entire, order of magnitude in stellar mass or radius. So really, when you say red dwarf star, like you're talking about really many, many different types of stars, and even individual red dwarfs have different levels of activity and different magnetic properties. And so an example of a more quiet red dwarf would be LTT 1445A, which is, I believe, the closest transiting M-dwarf planet. It might be the second closest transiting M-dwarf planet. And it's another rocky planet around a slightly more quiet star. And up until last year or so, it was assumed that that star did not emit frequent flares. And then lo and behold, we pointed the Chandra Space Telescope at it. And Alexander Brown, also here at CU Boulder in the office behind mine, found that indeed it actually does flare. And so all three stars in that multiple star system flare, including the exoplanet host star. But it does seem like its flare rate is significantly lower than Trappist-1's.
It's interesting how situational it is. To compare the red dwarfs, let's move up a little bit to the type K, the orange dwarfs, which we could also presumably look for, but I guess that gets a little bit more glare and more difficult to try to characterize. But are those active, as far as we know, as far as flaring, or do they calm down? At what point does it start looking more like the sun as opposed to Trappist-1?
In my field, when we say solar type, we include early K dwarfs in that designation. Like a very late K dwarf, we would think of as still a red dwarf. But when we say solar type, we would say, oh, Epsilon Eridani, a young solar type star, even though it's actually a K dwarf. The problem with those stars is that if you're interested specifically in the atmospheres of planets the size of the Earth, you lose the signal to noise that you need to detect the atmosphere. If you're interested in, say, very, very young planetary atmospheres like AU-McB, which are hydrogen-helium dominated, those you can still detect around a K dwarf. But if you're interested in an Earth-sized planet, and the habitable zone in particular, your only hope are the red dwarfs with current technology.
So let's stick Earth in orbit around a red dwarf and see what it might look like. And say it's within the habitable zone of that star, and it's Earth, or early Earth, however you want to characterize it. Is Earth going to be able to withstand the onslaught of these flares, or is it going to strip the atmosphere away and we would have no Earth? We would just have a rock, an atmosphereless rock. Or do we even know? I mean, do we need to look at the further stars in that system to even know?
That's a really good question. I'm not sure that there is a definitive answer at the current time. And there are different astronomers, I think, that probably have different leanings on that question. Some models show that if you just dropped Earth around a red dwarf star, that within 100,000 years, it would have fully lost its ozone layer, and then the surface would be bombarded by germicidal levels of UVC radiation. Other models show just that the atmosphere would change dramatically, but maybe reach a new equilibrium. Other models might suggest, again, a bare rock scenario, as you'd mentioned. It would certainly have a major effect, but whether that effect would be prohibitive of life or just a stressor for life is something that I think has not been fully shown.
Yeah, and you always have the question of underground and ice shells and all the other things that can happen situationally. But back to that idea, that word, germicidal. So that's surface life, and it would basically just kill it off. Now, what is that? Is that ultraviolet doing that, or is it just a mix of everything? I know with like a type F star, we're way far away with that, but those things would bathe anything in their habitable zones with ultraviolet. And obviously we use ultraviolet to kill Earth life. So, and without an ozone layer, we would have serious problems on this planet. So is that what's coming off of the red dwarf? Is it an ultraviolet problem?
Yes, it's also an X-ray problem, but specifically ultraviolet C would be sufficient. In fact, I actually just grabbed a paper in the middle of the COVID-19 pandemic to see what levels of ultraviolet C they were using to clean rooms during the height of the pandemic when we didn't fully understand, how the virus was spreading. And then I compared those levels of radiation to what was reaching the habitable zones of these M-dwarf planets, and the numbers are actually very comparable.
That's amazing. So we could actually speculate and say COVID-19 could not survive on an exoplanet around.
I had slides in my conference talks on that exact topic. I would pop up a picture of the COVID-19 virus and then show what the germicidal levels to kill the D90 dose that would kill 90% of those organisms were, and then I would just plot it compared to the flares. And it's a fun plot. Interesting.
So the other problem is that, of course, we look at these and we say, well, liquid water could exist here, but that itself is situational, right? In other words, you're going to have certain other conditions present at these worlds, like atmospheric pressures and things like that, for this to happen. Does the star interfere with that, with its flaring? In other words, can it just simply flare so much and change its conditions so much over the course of a day that you just can't get to an equilibrium where you would have liquid water?
That is also a really good question. There's some models right now that are being run by my colleague Laura Do Emerald. And her work is to explore what the long-term effect of the X-ray and UV radiation of these flares would have on the retention of water in a terrestrial atmosphere. And what she's been finding is that you can lose several Earth oceans of water over geological timescales due to these sorts of events. So if those models are accurate, then that could potentially be problematic.
Yeah, because you're looking at disassociation. Now, what about hothouse worlds, Venus worlds? Can these form?
Steam atmospheres.
Yeah, can you end up with that situation in a system like this? More likely, and would it? Let's transport Venus to the red dwarf. Would Venus be more robust in that environment than Earth would?
That is a really good question. So when we think about exo-Earths, I think that that's actually a little bit misplaced, as you mentioned. I think Venus is probably a much better analog for the types of atmospheres you'd be likely to see around a red dwarf. Because if you were to drop a habitable planet from our solar system around a red dwarf, what would almost immediately happen would be either a moist or runaway greenhouse effect that would be pumping all of this H2O high up into the planet's atmosphere. And at least during the pre-main sequence, it's predicted that that atmosphere would survive. But over the course of the star and planet's coevolution and lifetime, it's quite possible that it could be lost.
We just need a bigger data set than we can. Well, at least though, we're getting to the instrumentation that's allowing for that. Now, future telescopes and the search. I know we're building a lot of gigantic ground-based telescopes, and we're building survey telescopes. Like the Vera Rubin Observatory. Will that help in your characterization of these flares? In other words, can you look at those all-sky surveys and see the flaring data there?
Unfortunately, not with Rubin, but there are a lot of other sky surveys that are giving us excellent statistical information on the rate of flares and then the energies involved in stellar flaring. One of those, obviously, is NASA's TESS satellite, and then other observatories are observing some of these flares simultaneously. During my PhD, I was working with a system called Everyscope, which is an all-sky blue optical telescope, and then TESS is an all-sky, essentially red optical system. And so some of the time, those two telescopes are overlapping each other when flares occur. We can use those to try to estimate how much UV radiation might have been released. Some flares are observed simultaneously with TESS and NASA's SWIFT satellite. There are CubeSat missions currently being planned that will observe simultaneously in the optical and in the UV, or in the optical and in the X-ray, and so forth like that. In terms of making measurements from the ground, I think some of the best atmospheric constraints, not on the flares, but on the planetary atmospheres, will actually be extremely large telescopes like the TMT. The problem with Rubin is the cadence. It doesn't really, so flares evolve on timescales of seconds to minutes, and Rubin, I think, revisits the same field much more slowly than that. So you would only get, one data point rather than the kind of cadence you'd need, and that's why TESS is so much better.
Were you able to do anything with Kepler in this regard? Or is that just too different of a telescope? Because that had a cadence of, every 33 minutes, something like that?
It also had a short cadence mode of 1 minute. The nice thing about TESS is that it's at a native cadence of 2 seconds, and plenty of flare stars have been observed at 20-second cadence by TESS. I'm sort of pushing for them to release some of that 2-second cadence data, but it's a really big ask because of the amount of downlink bandwidth that they have available. And they usually just combine that data on board and throw most of it out once they've combined it into the 20-second cadence mode. The problem with Kepler is that it didn't actually observe that many red dwarf stars. It observed lots of G and K stars by design, because it was trying to measure a quantity called eta Earth, or how frequent Earth-sized planets are around sun-like stars rather than red dwarf stars. But still, there were some constraints from Kepler for red dwarfs too, and I would refer you to the work of Jim Davenport and Yang et al. 2018 and several other papers that do measure flare rates using Kepler.
Interesting. So, all right, just out of curiosity, what is the calmest type of star on the main sequence? And I'm not talking about when you get off the main sequence and you see things like Betelgeuse doing its thing, but it's getting ready to explode at some point. But on the main sequence itself, what is the most quiescent type of star? Is it type G?
I think so. I think long-term, our best chance of detecting a biosignature is probably going to be a planet orbiting a G-dwarf star, and it's probably going to be a next generation direct imaging detection. So I think we're probably many decades away from that, but that's what I think is actually the most likely.
Yeah, and many decades it's important to say that because there's only so much to work with now because this is a developmental process. In other words, one instrument leads to another, Hubble leads to James Webb, and capabilities change. For example, James Webb being not ideal for actual exoplanet searching. It's designed to look at ancient galaxies, things towards the beginning of the universe, but it does give infrared data on exoplanets that we can work with. Can we design something in the future that's specific to characterizing the atmospheres of exoplanets? Can we build your ideal telescope to look and characterize both the flares, but also the exoplanets?
So the ideal system would have been a concept called HabEx, which unfortunately was not promoted by the NASA, or rather Astro 2020 Decadal Survey. So unfortunately, that was not promoted in this current cycle. So maybe it will receive promotion in a few decades, but because we have a different concept called the Habitable Worlds Observatory that is being promoted, and there are other concepts that are also being promoted. We're putting funding into those. Those don't quite have the capability to do with the things that I'm talking about. So it could quite easily be a very long time. People that haven't even started their PhDs yet will, in my opinion, probably have retired by the time that we actually put the funding into doing that.
Unless it all changes and JWST finds a characterized atmosphere that's looks really good, and gives a compelling reason to start studying exoplanet atmospheres above and beyond what we do.
Yes.
And it could happen, we don't know.
Unfortunately, there have been a lot of somewhat questionable claims of, habitability or biosignatures. Even with JWST, you probably are aware of the claim of dimethyl sulfide or DMS in the atmosphere. It's not enough. And they also only used one. We're still at the very beginning of working with JWST data. So the gold standard right now is to try multiple independent pipelines and see if a result survives. Only one pipeline was presented in that particular paper. So, in the raw data underlying the paper hasn't been publicly made available yet. So there's no way to check that it survives even, a different reduction. So I would like to see some more robust, detections of that sort of thing too.
Know your instrument. So we're still in the process of learning JWST, right? In other words, you got to know the ins and outs and the oddities of the instrument itself. And that's not necessarily quite the case yet. It's still brand new.
It's still brand new.
Now, when we look at these exoplanets around like Trappist-1, and we've already found that the inner two, to my knowledge, have no atmosphere that we can detect. What happens if we detect no atmospheres on any of them at all? And they're all just, Mercury-looking worlds that might have wispy, almost non-atmospheres or not worth mentioning. Would that tell us, would that give us enough of a sampling to say, yeah, all red dwarfs are probably not habitable, probably not a habitable class of the star? Could we infer that just from that single star, since that being our best candidate? Or, say we look at 3 candidates and they're all the same, stripped atmospheres. Is there any hope after that? Can a red dwarf planet reacquire an atmosphere or something like that? Or is it just, would we be able to say type M? Not likely.
So there are a lot of sub-questions within that one question. And the first one I'll start with is actually a statistical question, which is that it's very, very difficult in a statistically robust way to say anything with a sample size of 1. That's actually the big problem we have with how often, does life spontaneously arise in the universe, is if you only have a sample size of 1, it's consistent with priors of both extremely common and extremely rare. So the same sort of issue might potentially apply here. For example, there are other factors like, say, the stellar metallicity. Maybe the metallicity of the formation environment of the star in the planetary system has something to say about whether atmospheres might be retained or not. So I think we need more than just one system. Once you get 2 or 3, the statistical question starts to become a little bit more tractable. And obviously, the more in the sample, the better constraints that you can get. The second part of the question is, if we don't detect anything specifically with JWST, I don't think that rules out the existence of any atmosphere on these worlds. It simply rules out the existence of a thick, easily detectable atmosphere, as you mentioned. So there could still be a tenuous atmosphere, or just the temperature pressure profile of the atmosphere just might be something different than we're expecting. We really need a better telescope than JWST to say conclusively Mercury, 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 all the way out. If we don't detect any atmosphere on any of the planets, you are correct that would certainly be consistent with the data. And that, leads to the sorts of talks that like David Charbonneau would give about talking about, God-forsaken worlds orbiting small angry stars or things of that nature. But yeah, I think we would need a better telescope, maybe a TMT or another ELT to be able to answer that particular question.
Now, this may be outside of your wheelhouse, but this is something that I wonder about, is tidal effects from stars on these kinds of planets. In other words, could the Trappist-1 systems, the ones, the members that are really close in there, could they be, because we know that they're probably tidally locked, so they're obviously under gravitational influence from that star being so close to it, but could that be driving volcanism on those worlds? In other words, could we detect gases that aren't indicative of life, but are indicative of volcanism? And so, but I'd probably need to ask an earth science, a planetary scientist expert on that. But it's interesting because there are other questions that can be asked about these systems, which is kind of what I'm pointing out, is that we know almost nothing right now until we really study these things and think about it based on the JWST data. Wouldn't you agree? I mean, there's a lot more to be learned here than just habitability.
Oh, absolutely. I mean, as a scientist, that's the best place to be, in my opinion.
It really is. So what's next? What is the future of characterizing and sort of mapping out the flare profiles of red dwarfs? I mean, where do you go from here?
There are a couple directions you could go, and the one I'm going to choose to go down to answer this particular question is the question of how to remove the flare contamination from our ability to look for atmospheres in the transit spectra of these planets. And the reason I'm going to go there in part is because of the paper that we had discussed earlier, where we were able to characterize the flare spectrum with JWST for the first time in order to then characterize and remove that spectrum from the observations and recover better signal for the transits. And the reason I want to mention that is there's a correlated paper that was actually the key paper from our larger collaboration, which was led by Olivia Lim at the University of Montreal. And her team at Montreal found, no detection of an atmosphere for Trappist-1b, but what they did find was a lot of evidence of stellar variability between each of the visits that they made to the star. And so there's this very, early, before we get to the really exciting questions of like, what does the atmosphere look like? We need to answer maybe the simpler and more mundane, but extremely challenging question of how do we account for all of the changes from the star in order to best analyze the signal of the planet? That's hard. And so I'm doing a lot of thinking right now about how to correct not just the effects of the flares, although certainly including those, but also what can we do to help minimize the contamination from star spots, both occulted and unocculted. Have you heard of a term called the transit light source effect?
Explain it.
So the transit light source effect is a complication that arises when doing transmission spectroscopy of an exoplanet atmosphere. Because in order to look for a planet's atmosphere, you have to have a comparison spectrum. So you use the disk-integrated pre-transit spectrum of the star before the planet passes in front of the star. And then you compare that with the spectrum when the planet is in front of the star, subtract the two, and what you're left with should be the planet's atmosphere. And the problem is that any difference between the pre-transit integrated spectrum of the star and the spectrum of the path that the planet takes across the star, which we call the transit chord, any difference between those two things is going to induce contamination. And that's something called the transit light source effect. And so that effect can be as mild as just getting some extra data processing that's required or getting the amount of material incorrect. It could be as severe as detecting molecules that aren't even present in an exoplanet atmosphere. There are questions right now about whether water vapor that's been detected in, several M-dwarf planet atmospheres is actually from the atmosphere, or whether it's water vapor that's formed in cool star spots that are just not occulted by the planet.
Yeah, how would you tease it out? How would you tease it out?
Great question. So I'm actually working on a JWST proposal I'm hoping to submit in a couple weeks, in part to try to do this. Of course, that's always subject to the, telescope allocation committee deciding to grant time, which is really competitive. So I may have to try a couple cycles to get this through. But what you need to do is to understand, I think, 3 different sources of contamination, and there are different approaches that can be used to address each of them. Starting with occulted star spots. The benefit of those is that they're the easiest, I think, to pull out because you get a symmetrical rise in the transmission spectrum from an occulted spot that it has a very characteristic shape, and it doesn't usually last very long. So you can identify and remove that data from your analysis and then ask, if I include it or don't include it, do any results change? Check. Okay, we've got the first one. The second one is a little bit harder, and that's unocculted spots. So the best way I can think of to handle that is to think about the way that star spots evolve in time. So A star spot has a life. It doesn't last forever. And that life is very dependent on the type of star that we're looking at. So take TRAPPIST-1, for example, the spot decay lifetime over which a spot will, significantly change or vanish is known to be about 110 days. And, I was actually just not thinking of TRAPPIST-1. I was thinking of AUMIC for that particular case. For TRAPPIST-1, the spot lifetime is probably still consistent with 100 days, but it could be as short as like 30 days based on the spectral type of the star. And so what you'd want to do is to time your transit observations of the star such that the same side of the star is facing you each time, so that when you're looking for what's changed, what you're seeing change is not just the face of the star that you're observing and therefore different spot properties. And you're also going to have to carry those observations out back to back before the spot itself manages to evolve. So what you might want to do there is think about, okay, we know that transits are going to occur after our initial observation every, say 18 days for like TRAPPIST-1 G or H or F. And so we know what that period is, and we know what the rotational period of the star is. And so you can just line that up to figure out, okay, we want to observe at this phase and at this phase and at this phase and at this phase. And if we go too far out, then you risk the stellar surface actually evolving. But if you do it quickly enough, you should be able to get multiple measurements at the same phase to account for the issues from some of the spots. And then of course there's modeling efforts that can go into that too. Better modeling of star spots and understanding what the surfaces of very active stars look like will increase our modeling power for the data that we do have. And all these techniques are not mutually exclusive. You can combine them. And then of course for the flares, we want to continue to better understand what the near infrared and mid infrared spectra of flares look like. As you may have noticed when you probably skimmed the paper that we just released, we both used a very simple Planck function fit, which actually fit the data really well. And that's what we used to correct the transmission spectrum and the transit light curves of TRAPPIST-1F and TRAPPIST-1B. But we also ran a actual physics forward model of a solar stellar flare and then fit that to some of the data that we observed, and it did not fit as well. And we suspect the reason for that is that we did not include some very relevant physics that's less important for a solar flare, but might be more important for an M-dwarf flare. And I could go into more details of that if you're interested, but by improving those sorts of models, we might be able to get the amount of flare contamination removed in a more robust and maybe model independent way. So those are some of the things I've been thinking about.
Now, within this, just as an aside, do we see any evidence, especially in this data, or any data that you've seen, for cycles? We know the sun has an 11-year cycle, but do red dwarfs appear to also have cycles, or are they just constant?
They do have cycles. So there's work that's been done by Todd Henry's group, I believe at one of the universities in Georgia, with the Recon telescope over many decades. And there's a grad student there, Andrew Cooperis, who's been working on identifying and characterizing those sorts of cycles. And indeed, they do seem to have multi-year sorts of cycles. Another example would be Proxima Centauri, which has years of X-ray monitoring. And there's a candidate 7-year cycle that was detected in NASA SWIFT data by Warglen et al. 2017.
How good of a candidate is Proxima B? So in other words, can we, it's obviously the closest one. Can we look at that, or is there disadvantages in that particular system that prevent us from doing this kind of, science that you're doing with TRAPPIST-1? Can you look at that red dwarf and have a comparison star because it's just right next door?
So TRAPPIST-1 has 7 transiting planets, and unfortunately, Proxima has 0 transiting planets. But Proxima is close enough till a future extremely large telescope may be able to directly image it. So I think the best chance for characterizing the atmosphere of Proxima B would probably be direct imaging. But if you just mean in terms of like the proxies of, can we understand flares from Proxima and then compare those flares for flares against, say, TRAPPIST-1, is that more of your question?
Yeah, in that. And then I've got a follow-up on that one. But yes, it's just as far as comparing the stars.
Yes, but with some major caveats. Yes, they are generated by very similar physics, and they're both late-type M-dwarf stars. But one of them is an ultra-cool dwarf, and there's some evidence that the particle acceleration environment that drives flaring may be a little bit different for ultra-cool dwarfs than it is for, an M6 late-type dwarf like Proxima. And the caveat example I will give is the multi-wavelength. So flares emit across the entire electromagnetic spectrum, all the way from the hard X-ray all the way into the millimeter and the radio. And this is true of the sun too. And so we can look at the multi-wavelength properties of solar flares and look at the exact same size of flare from another star, say Proxima, and we'll see that, say, the X-ray emission of the two flares is identical, but yet the millimeter emission of the flare from Proxima is 1,000 times higher than the same size event from our sun. And that might imply that there's something very different about the magnetic fields that are accelerating those particles that produce what's called gyrosynchrotron emission, which is what we think we're observing in the millimeter and the radio part of the electromagnetic spectrum. And so if there's any sort of if there's that much of a difference between the sun and Proxima, it raises the question, could there also be differences between, a star like Proxima, which is an M6 dwarf, and a star like TRAPPIST, which is an M8 dwarf? And indeed, there's some very tantalizing evidence that that is the case. A lot of these very, very late stars like TRAPPIST-1 are what are called radio bright, which means that there might be what's called electron-cyclotron maser instability, or ECMI emission. Whereas for Proxima, we don't really see as much evidence for that particular type of emission. And so it seems like there may be some population differences even there. And I would refer you to a paper by Peter Williams et al., I think 2014 or 2016, which does a deep dive into that particular topic.
Now, my last question for you is this. Is it possible in the future, as we directly start imaging exoplanets, and we have some hope of that, as you just mentioned, can the flares be used to our advantage in that case? In other words, when a flare cooks off at a red dwarf, does it brighten the planet that you're trying to observe? And if you watch long enough when you've got several flares a day, can you see the planet better when the flare is cooking off as opposed to when it's not?
I think that makes sense. My main question would be, what's the albedo of the planet, and what sorts of contrast enhancements would you be able to detect? I don't know the answer to that particular question, but I do think that that's absolutely something that could potentially be used as an observational signature.
But that's interesting in and of itself, because if you could start characterizing the albedo of an exoplanet, then that could get really interesting really quickly, because we're sitting on a planet that is high albedo due to clouds, correct?
Yes.
All right, Doctor, thank you for joining us today. And I want to check in again as you continue this research, because the red dwarf system is just fascinating because they're just so accessible to us as opposed to, a lot of other types of stars right now. And this is where we start. This is the starting point in characterizing the stars of the galaxy and asking questions about their habitability, but also learning about the differences between stars. And these stars, the red dwarfs, turned out to be very different than I think anyone ever realized. And they are far more active and interesting than what I could have imagined 30 years ago.
Absolutely. I wasn't doing this 30 years ago, but I can imagine the satisfaction of watching the evolution of the field from not even knowing that there were, planets orbiting every star to measuring what's in the atmospheres of those planets.
Well, here's how this went down. Everybody was, before, when I first got into this in the late 80s, we knew that exoplanets almost certainly existed, but we hadn't seen one. And the first one we found was around a pulsar.
Yes.
And that no one expected. All right. Thank you, Doctor.
Thank you. I appreciate your time. And thank you for a wonderful conversation.
Yeah, thank you.
Have a good afternoon.